Respected dignitaries, esteemed faculty members, and my dear all friends, I am Tejashree from EEE department. So today I am going to talk about parallel RL circuit transients in motor starting applications. So let's get into it. Introduction to parallel RL circuits in motor starting. Parallel RL circuits are commonly used in motor starting applications to control inrush currents. Understanding transient behavior is essential for effective motor control and protection. This presentation covers the fundamentals of transient analysis in parallel RL circuits during motor startup. So let's have a word before we get into this. So, when electrical motor starts, they draw very high current. This sudden change creates transient behavior in circuits. Understanding this is very important because it affects motor life, causes voltage drops, can damage electrical systems. What is parallel RL circuit? The parallel RL circuit consists of a resistor R, inductor L connected in parallel. Key idea: voltage across both components is same. Current splits between resistor and inductor. What are transients? Transients are temporary changes in current or voltage when a circuit is switched on or off. In motor starting, current doesn't instantly reach steady value. It changes over time. Motor starting and RL behavior. When motor starts, it behaves like an inductive load. Initial current is very high in rush current. The inductor opposes sudden change in current. So the current increases gradually. Energy is stored in magnetic field. The transient current in RL circuits follows an exponential form where I of t is equal to current at time t, I is equal to final steady state current, T is equal to time constant. Time constant is it tells how fast the current reaches the steady state. Rules: when T is equal to tau, current reaches 63% of final value. Where after 5 tau, system reaches steady state. Behavior in parallel RL circuit. In parallel RL, total current is equal to sum of branch currents. Resistor branch current flows instantly. Inductor branch current increases slowly. This causes uneven current distribution, transient effects. Applications in motor starting. Used in industrial motors, pump systems, conveyor belts, HVAC systems. Helps in controlling inrush current, protecting equipment, improving efficiency. Problems: high starting current, voltage dips, heating. Solution: star delta starters, soft starters, use of resistors. So let's get into the presentation. Basic components of parallel RL circuit. The circuit consists of an inductor and a resistor connected in parallel across a power supply. The motor stator winding can be modeled as an inductance with some resistance. Additional components such as circuit breakers and protective devices may be included in the practical setups. Significance of motor static transients. During startup, motors experience high inrush currents that can damage components if not properly managed. Transients determine the voltage and current behavior immediately after circuit energization. Proper analysis helps in designing circuits that minimize stress and improve reliability. Transient response in parallel RL circuits. Transients are temporary responses of the circuit to sudden changes like switch on. They involve exponential variations of current and voltage over time. The response depends on circuit parameters such as resistance and inductance. The circuit's behavior is described by first order differential equation. So this is basically dou by dou S is equal to R times I of t plus L dou by di by dt. Solving this equation provides slight insight into current and voltage evolution during startup. The initial conditions influence the transient response significantly. The time constant. The time constant characterizes how quickly the current reaches the steady state. The larger inductance or smaller resistance, it results in a longer transient period. Understanding this helps in designing suitable starting controls. As you can see the graph here. Current growth during startup. The initial current is zero when circuit is energized. Thus, current increases exponentially towards a steady state value governed by the supply voltage and circuit resistance. Voltage across inductor and resistor. Voltage across inductor and resistor initially equals to the supply voltage and decreases over time. The resistor voltage starts at zero and increases as the current builds. The sum of voltage across L and R equals to supply voltage all the time. Steady state current. After the long time, the transient effect dissipates. The current reaches the steady value. The inductor behaves like a short circuit at steady state in DC conditions. Effect of circuit parameters on transients. Increasing resistance reduces the time constant, leading to faster transient responses. Increasing inductance prolongs the transient periods and reduces initial current. Proper parameter selection is crucial for controlling startup currents in motor applications. Impact on motor starting. High inrush current during startup can cause voltage dips and mechanical stress. Transient analysis aids in designing soft start and reduced voltage starting methods. Mitigating transients ensure smoother motor operation and longevity. Protective devices and their role. Circuit breakers and relays are used to limit the effects of transient overcurrents. Proper coordination of protective devices prevents nonsense tripping during startup. Transient analysis informs the setting of protective device parameters. Practical considerations in motor starting. Soft start devices such as auto transformers and variable frequency drives reduces transient effects. Adding reactors or resistors can limit inrush currents during startup. Monitoring transient behavior helps optimize starting procedures. Modeling and simulation techniques. Circuit simulation tools like SPICE provides detailed transient analysis capabilities. These simulators assist in predicting circuit behavior before physical implementation. Accurate modeling considers non-idealates like parasitic resistance and inductance. Case study. Motor starting with parallel RL circuit. A typical case involves 10 HP motor with known circuit parameters. Simulation predicts current peak and voltage drops during startup. Results guide modifications to ensure safe and efficient motor operation. Mitigating transients in practice. Using control switching methods can reduce transient overshoots. Employing reactors or RC snubbers helps absorb voltage spikes. Proper wiring and grounding practices are essential for transient suppression. Summary of key concepts. Transients in parallel RL circuits are characterized by exponential and voltage changes. Circuit parameters significantly influence the duration and magnitude of transients. Applying these principles improves motor starting reliability and reduces electrical stress. Future trends and developments. Advanced power electronic devices enable precise control of motor transients. Integration of real-time monitoring improves transient management. Ongoing research aims to optimize starting methods for energy efficiency. Conclusion. Understanding the parallel circuit transients is vital for designing effective motor starting systems. Proper analysis and mitigation techniques enhance motor lifespan and system stability. Continuous advancements in technology will further improve transient management. Before ending, let us see the summary of all points we have discussed. To conclude, parallel RL circuits show transient behavior during motor starting. Inductors delay current rise. Time constant controls response speed. A proper design helps protect systems. Understanding transient is essential for safe and efficient motor operation. Thank you for listening. I hope this gave you a clear idea of parallel RL circuit transients in motor starting applications. And these are references. Thank you for watching. We are grateful for your interest and hope you enjoyed the presentation. Thank you.